is you have a domain which is maybe in R2, but more generally in Rn, and your function sits on it, something like this. And if we were to just look at the level sets and maybe look at those down on the domain, when would we see something like this? And what we did yesterday was we looked at a really classical proof for a very simple case here. So the case when f of u is equal to lambda u, and lambda here is an eigenvalue. And then we have the result of Braskamp-Leib that this property holds. And in fact, what Braskamp-Leib result shows is not exactly that the level sets are convex, because that's a very weak property. They show a slightly stronger property, which is that the function u is actually log concave. So log of the function is concave, and that's a little bit stronger than convexity of the level sets, but it implies it. So this is called quasi concavity. And the proof I had there was one that appears in a paper of Singer, Wong, Yao, and Yao. And in that proof, we kind of had some kind of interpolation between this setup here that we're interested in and a known setup on a ball, and we smoothly interpolate between the two and say, okay, if there's a point at which this property fails to hold, then we derive a contradiction. And this proof from Braskamp-Leib is somehow in the spirit of what's called constant rank proofs. And so let me write a little bit about those. So these are associated. A lot of this work was originally done by Korver. But the idea here is to show that the Hessian has constant rank. And then you can, and the way that you do this is sort of kind of homotopy techniques. And anyway, you show that the Hessian has constant rank, and then it kind of inherits the rank it has on the boundary, which we've already seen. It's kind of quite clear, and it inherits the convexity property of the boundary, and that kind of propagates to the interior, and so you get this property. But it's somehow, because we use these, it uses this topological proof, and really it's all about continuity. So it's somehow in the spirit of this previous proof that we saw of Braskamp-Leib. So I'm not going to talk any more about that, but it's kind of a really nice technique. And so what I'm going to do today is look at a different group of ideas, and these are called two-point concavity functionals. So let's write that. So if we recall the very classical notion of concavity, so it's funny because, you know, I write use concave if A, and then the next time there's a definition which I'll use is use concave if B, and B looks completely different. You know, there's hundreds of different, maybe not hundreds, I'm over exaggerating there, but there's so many different ways of describing concavity or convexity. I mean, it's such a strong and central property that you can think about it in a lot of different ways. I mean, every one of them is interesting and, you know, really, really nice. I won't say that every single one of them is useful, but I'll have to say that I haven't seen a definition of concavity that I don't like. So here we can say that U is concave. This is the one I'm thinking about right now. If U of t plus x plus 1 minus t y is greater than or equal to t u of x plus 1 minus t u of y. So the picture here is you have a graph, something like this, and if you have 2 points, x and y, then the value of u at a intermediate point, which is the point on the left-hand side here, is going to be greater than the sort of linear interpolation between the two endpoints. Now, this works for all t 0, 1. And so what we can do is we can take this sort of inequality here, and we can use this as a way of detecting concavity. So we try to prove, we put everything on one side and we try to prove that this inequality holds directly. And the techniques here are sort of maximum principle type techniques. So there's yet another characterization of concave functions here. And this is a kind of specialization of the one I've just written down. And we say U is midpoint concave if, and here's a definition, right, C of x, y is equal to U of x plus y on 2 minus a half U of x minus a half U of y. So this is all x, y, omega. This one should also be for all x, y, and omega. So this is just like the previous one, except now we only care about the point that's exactly in the middle. So instead of for all the points, we just care about this difference here, where this is the midpoint between x and y. Sorry. Oops, lost my graph. And so this looks a little bit cruder. It's just looking at single point, but it turns out that due to a result of Jensen's that actually midpoint concavity implies concavity.
Sorry, Julie, maybe you mean that the C is positive.
Oh yeah, I didn't write down the condition, right? So let's write C is greater than 0. Thank you, thank you. So let's sort of highlight this. C is positive. So midpoint concavity implies concavity. So I'm going to sort of show you how you can work with this midpoint concavity, but first I'll just mention some other 2-point techniques. So here is a different one. This functional detects quasi concavity. So we have Q of xy, which we define to be U of, again, the midpoint minus the minimum of U of x, U of y. And Q greater than or equal to 0 now implies U is exactly the same as U being quasi-concave. And so there's one more. This is a more recent one. And it goes like this. This is what we call a modulus of concavity. Technique. And we define sigma of S. Now, this one is kind of a quantitative concavity. So for every parameter sigma, a positive parameter sigma, we define sigma of S is the supremum of kind of a directed difference in the derivative. So let me write du as y minus du of x. And this is the vector that runs between them. And we take the supremum over all points that are y minus x. The distance between y minus x is equal to 2s. Okay, and then if sigma of s is less than or equal to 0 for all s, I guess s has to be in 0, and the largest it can be is the diameter, 2, then U is concave. Okay, and so this quantity in here, you can think of this as a difference quotient for the second derivatives of U. And so if you see 2, then you can go back to the usual sign on the Hessian definition of concavity, or you can integrate this up and get the sort of C0 definition of concavity there. So let me just stop there and see if anyone has any questions or comments, because I know there's some experts there. Okay. All right, so I'm going to use the midpoint concavity definition here. So let's write this maybe as a little heading. And let me just give you a few names. So this is related to ideas of Caffarelli. And Brook. And particularly Kurova in the early 80s. And there's also another proof of results due to Kennington. And there's a really nice treatment of this in the book of Cavol. So what I'm going to prove here is a concavity maximum principle. And let's okay, so my conditions here are that omega is some sort of convex domain as before, and U is C2 in omega and C1 up to the boundary. And this kind of proof will work for a really large class of degenerate elliptic equations. So we could sort of write something very general here. But I'm not going to, I'm just sort of thinking about time and so on. So I'm going to replace this left-hand side with just a fairly simple version of this. I'm going to write, and if we remember the equation satisfied by log of U in the eigenvalue problem, we remember that we pick up some sort of nonlinear second derivative terms. So I'm going to write C u squared like this. My C's some positive real number. And so the reason why, right over here, okay, so in that eigenvalue case, then B will just be some positive constant. Okay, so satisfies this. And the conditions on B are this right-hand side here. Firstly, B is decreasing in the third variable. It's jointly concave in the first two variables. And that means that if we have B of x plus y on 2 and a half, say v1 plus v2 for just some numbers v1 and v2, and some point p here, this is going to be greater than or equal to a half b of x v1p plus a half b of y v2p. And you can see here that I'm using a midpoint definition of concavity again. And the third condition is probably most important, well, crucially, is strictly decreasing. In the second variable. So that's the setup, and the statement of the theorem is that then C, which we'll write down again, C of xy is this midpoint concavity, cannot obtain or attain an interior negative minimum. Okay, so if C does have an interior minimum, then it has to be positive. And as long as we can rule out C being, or as long as we can ensure that C is positive on the boundary, then this will mean that C is positive everywhere. Okay, so that's the statement of the theorem. And oops. So let me give myself a little bit more space for shrinking everything. the sort of big picture here is well, one can then prove that I just wrote this very roughly because I'm not going to do this in detail. Oh, that's really right. And together, this will prove that C is greater than everywhere, C is positive everywhere, and U is concave. So, in fact, we need some extra conditions on B here. I think we need B is positive. So that's kind of how this concavity maximum principle is used. So the calculations on the boundary are kind of fun as well, but I'm not going to go into them. I'm just going to look at what's going on with C in the interior, because that's the sort of central idea here. So let's prove this. Okay, so we can just highlight this definition of C. That's going to be so important. So CMP here is the concavity maximum principle. So this is just a really classical maximum principle type of idea. So let's suppose that C attains a minimum at an interior point xy. Okay, so our goal here is to show that at that interior point, C of xy is going to be greater than 0. And my screen here is not big enough. I want to keep C on it. Okay, there we go. So we can see C at the top. So we do what we usually do when we're using maximum principle, is we just calculated a whole bucket of derivatives, first derivatives and second derivatives. And the thing that we should keep in mind here is if we have our domain omega, C is defined on 2 copies of omega. So there's some point x here and some point y there. I guess if x is equal to y, then C is going to be equal to 0 anyway. That's straightforward. So we can define derivatives when we move x around, and we can also define derivatives by looking at what happens when we move y around. So let me write those in kind of this way. So let's look at derivatives with respect to x variables of c. So this is going to be a derivative of u of x plus y on 2 in the first case. So this is going to give us a half du evaluated at x plus y on 2. So here's the line between x and y, and this is x plus y on 2, this midpoint. And because I'm going to use this a bit, I'm just going to call that midpoint z. So this is going to be z here. Okay, and we also have a derivative with respect to this u of x. So this will give us a half du evaluated at x. And our assumption that this is a minimum means that this is going to be equal to 0. We can do the same thing for derivatives with respect to y, and we'll get a half du, again evaluated at z, minus a half du at y. And again, this will be 0. And so there's already a lot of symmetry going on here. The derivatives at, so du at x is going to be equal to du at z by this first one, and that's going to be equal to du at y. So in particular, we notice that actually I'm going to use this like this. And just to reassure you that I'm going to use this, I'll give it a number, call it number 1. Okay, now we've done the first derivatives, we can calculate the second derivatives of c. And again, they're given by second derivatives, either at x or at z or at y. So let's write the ones that are sort of purely in x directions will be given by, the pen's gone very faint. This is given by, let's see here. So, oh no, we don't need C, we just need the first derivatives. Okay, we take first derivatives here. So we get 1 on 4 d2 u at z minus a half d2u at x. Same picture for second derivatives in y directions. And mixed derivatives, we just get that first term at the midpoint. So this will be 1 on 4 d2 of z. Okay, so if we assume we're at a minimum point, then the second derivative, so the Hessian of C, is going to be positive. And we can think about the Hessian of C as kind of this block matrix where we have this derivatives at the midpoint in all the positions. There's sort of 4 copies of that. But we've got another term too on the diagonals. So here we'll have minus 2 d2u at x, and here we'll have minus 2 d2u of y. Okay, so I mean this notation is maybe a little bit idiosyncratic, but this is a 2n by 2n matrix, and these parts here are little n by n matrices, or bilinear operators, I guess. And if we take this positivity of the Hessian here, we can look at what happens to this when we hit it with vectors either at, in the tangent space at x or the tangent space at y. And so the first thing we're going to do is look at hitting this with sort of 2 vectors that are the same at x and y. So here's E. So for any fixed E in Rn, so this is a direction, we have E write it like this. Here's E D2C E E. And we can sort of do this component by component, and what we'll get here is we get okay, so I'll maybe keep my 4 in here just to keep it consistent. So what we get here is we get 4, and we get an E hitting D2U at Z twice. This is a transpose here. Whoa. Minus, and we'll get 2 E d2u at x E, and we'll get a similar one at y. And the way in which we're going to use this is we're going to do this for a sort of set of n orthonormal basis vectors. So E is going to be equal to EI from I equals 1 up to n. And we're going to sum over these EIs. So what we're going to get here is, instead of sort of components of the Hessian, we're going to get the trace. That is the Laplacian. So we get, let me divide through by the 4's here. So we're going to get the Laplacian of u at z minus half the Laplacian of u at x minus a half Laplacian of u at y is going to be positive. Okay, that's going to be useful for us. And this happens not everywhere, but it's just at x, y. So this is just a consequence of this, our assumption that this is a minimum. And let's do this again. Oh, I'm going to use this, so we'll call it 2. So let's do this with now E and minus E. Hessian again, E minus E. So again, this is positive, but this time all the terms that have the Hessian evaluated at Z at the midpoint, these will cancel out because of these things appearing again on the cross, on the off-diagonal blocks. So what we'll get is, in fact, minus E d2u at x minus and again we sum over this basis EI, and we'll find that the Laplacian of u at x minus Laplacian of u of y satisfies this inequality. So are there any questions so far? Is this kind of making sense about what I'm doing here? I guess there's silence. That's, I guess, a good thing. All right. So actually, that's all the ingredients I need So the next step is I'm just going to write down the PDE at the midpoint. Okay. Okay, so here I've got b of x plus y on 2. I've got u of x plus y on 2. And I've got some length of the derivative. And I guess we're calling that x plus y on 2z, so it's a bit easier to write it like that. And so our PDE says that b is equal to minus Laplacian of u at z. And we possibly have this nonlinear term here. And this is good. Now, the first thing that we can do here is we remember that our first derivative condition said that all the derivatives at x and y and z were all equal. So let's use that. So I'm going to use C, and then I'm going to write this as a half u of x squared minus a half u of y squared. And this is going to be using, I think I called this number 1. Yeah, this was this condition here, first derivative condition. Good. Now I pay attention to this u of z, and in fact, we just had an inequality for that. It's number 2. So minus u of z is going to be less than minus a half. No, minus Laplacian at z will be less than the sort of convex combination of the Laplacians at x and y. Okay, so this will be less than or equal to minus a half u of Laplacian at u of x minus a half Laplacian of u of y. So this was using 2. And here we've just got those things that are untouched. And now we've recovered the PDE at x and the PDE at y. So this is equal to b of, well, a half b at x, u of x gradient of u at x plus a half b at y, u of y, gradient u at y. And this, again, we can replace the gradients at x and y by the gradients at z. Okay, so this is using 1 again. And then we remember that we had this condition on b, which is b is jointly concave in the first two variables. I think that was condition 2. And so this means that we can replace this by an inequality with b of x plus y on 2, a half u of x plus a half u of y. This will be u of z. This is so yeah, I called that condition II. And then we're kind of done. So let's look at the complete calculation here. So we've got b at x plus y on 2. Let me try to write a little bit more darkly. We've got b of x plus y on 2, u of x plus y on 2, and then we've got this gradient, which we don't care much about. And this is less than the same thing, except in the second variable. Okay, so let's sort of highlight what's going on there in that second variable. So now we think back to all those conditions we wrote on B, and we recall that we said that B was monotone in that second variable. So let me, in fact, it was strictly decreasing in the second variable. So this means exactly that we have an inequality between those two terms that I've underlined. So we've got u of x plus y on 2 is going to be greater than a half u of x plus a half u of y at that point. So that exactly tells us that c of xy has to be greater than or equal to 0. So we're done there. And if c is a minimum, then c's if xy is a minimum, then this means that C will be positive everywhere or non-negative everywhere. So we're done. So that's a 2-point maximum principle there. And I don't know, I just find it really nice, you know, that you assume that you've got some maximum here, and then you kind of know everything about these equations. And as I said before, this will really hold for a very large class of quite degenerate elliptic equations. So to get the boundary principle, you need sort of a little bit stronger conditions to show that you can avoid having that you really do have concavity on the boundary somehow just from the shape of the boundary. But that's kind of the essence of the technique. So are there any questions? Or comments? Okay. So this is kind of old. It's now 40 years old, this technique really. I was going to prove something that sort of a newer technique, this modulus of concavity technique. And so this is something I worked on with Ben Andrews, and we were using it, or we needed it to work on some other problem, a problem about estimating the eigenvalues. And it turned out if you just had the log concavity of the ground state, then you could get an estimate, but it wasn't optimal. And to actually get a optimal estimate for actually it was for the difference of the first two eigenvalues, you needed to have some kind of quantitative log concavity estimate. And so that's why we did this modulus of concavity stuff. Now, usually when I talk about this stuff, I say, okay, this modulus of concavity stuff, it's super technical, and I'm just going to give it as a black box. So this is actually the first time I've ever talked about how this proof works. So hopefully it'll make sense, and hopefully you'll be able to see the parallels with this sort of much simpler 2-point technique that I've just done here. But, you know, feel free to jump in and say, hang on, what's going on here? Because I am going to gloss over some details. So let's give it a go. So let's start a new page here. Okay, so let's write down what we're going to do. And okay, so one of the complications here is that I'm going to introduce, I mean, we're kind of curvature flow, we're coming from curvature flow techniques, so we like things to be parabolic, and we like to use the parabolic maximum principle rather than the elliptic maximum principle. So I'm, you know, my equation here is that I'm interested in is the elliptic one. So let's write this as no, I don't want to have a general thing here. Sorry, my pen's gone very leaky. Okay, so it's the eigenvalue problem. We can also use a convex potential here, but let's keep it a little bit simple. Let's write W of x t. So we're introducing this time variable, and this is going to be given by log of e to the minus lambda t u of x. Okay, so this part here will solve the heat equation. And we notice that we're just scaling u of x by at each time by some constant. And so we're not really changing the shape of u at all. We're just kind of squishing everything down as time goes on. So anything we can say about the shape of this function at time t will also hold for the shape of the function at time t equals 0. So w here will solve dw dt is equal to Laplacian of w, and then we get this nonlinear term, which comes from taking the log. And we have some Dirichlet boundary conditions. And so I read this down before, but let's now write down a modulus of concavity, but it's going to be varying in time. So we're going to write, so previously we just wrote sigma of s. This is going to be sigma of s at time t. And this is going to be given by a half of this dw at yt minus dw xt. Sorry, my pen has really gone quite feral. So just excuse me while I fiddle around with this a little bit. So kind of the idea here is going to be that we're going to have this modulus of concavity, and we're going to show that it essentially is satisfying some one-dimensional heat equation. And we know kind of everything about one-dimensional heat equations. In particular, we know their long-term behavior in a fairly well understood way. So here we take the supremum, which I left out, and the thing we take the supremum over is all the points x, y, which have distance 2s from each other. So this is called the modulus of concavity. And again, you can think about this as the difference quotient, a difference quotient for the second derivatives. So our goal here is going to be able to show that sigmas is less than or equal to 0. And in fact, what we're going to do is show that so let's just write this down as something that we do, is we show that sigma is a viscosity subsolution for a one-dimensional heat equation. Well, maybe heat type equation. Sorry, I'm just thinking through about what level of technicality to put in without kind of freaking you out. Just my battery's about to go flat. Oh, good. Okay, now we're restored. Okay, so how does this viscosity subsolution stuff work? Well, the idea is we've got sigma, which is, we don't really know what it looks like, but perhaps something like this. And then we take another function, which we'll call phi. And phi will be a so sigma is going to be a subsolution if phi is greater than or equal to sigma everywhere, and at points where they touch, so this is, call this S naught, we have a differential inequality. So I haven't said what the differential equation here is. And I'll do that. I'll do that when the time's right. So that's, so let's work at this point where phi and S are equal. So at we recall that sigma is defined by this supremum. So let's take the 2 points where this supremum for sigma is attained. So let's take x naught and y naught be the 2 point, or be the okay. So in particular, we've got the difference between x naught and y naught is equal to s naught. And we have an inequality, which is that dw at yt minus dw at xt y minus x over y minus x is going to be less than or equal to 2 sigma y minus x 2 t. And then because we have this, because we have this, we get 2 phi here. So at the moment, phi is just any smooth function that touches sigma from above at this point. So we'll say what phi is later on. So what I'm going to do is, by analogy with the C that we defined in the previous proof, I'm going to define a Z, which will be like this concavity detecting functional. So let's define Z. Oh, there's something else I have to say before I do that. And the point is that here we have equality at x naught, y naught, and t naught. Okay. So let's define Z of x, y, and t. And pretty much throughout this, I'm going to suppress t, except where it's important, which will be almost never. So let's define Z to be sort of exactly given by this deal here. So we define this to be dw at y minus dw at x, y minus x divided by y minus x, minus 2 phi y minus x on 2. And what this thing here is telling us is that Z has a maximum at x naught, y naught, t naught. Now, just like in the previous proof, I'm going to completely neglect this story about what's happening at the boundary. So let's claim that this doesn't happen on the boundary. So unlike in the previous the previous proof, if you go and look up that boundary lemma for that 2-point maximum principle, you know, it's a beautiful proof and you're going to think, yeah, this is really cool. If you look at what's happening on the boundary here for this proof, it's really ugly and horrible and technical. So that's why I'm keeping it away here. But sort of the general idea is the same. You know, we've seen that you know, we do have quite strong boundary convexity for this problem due to so we have strong boundary concavity due to the convexity of the boundary, and that's kind of the moral of that's giving us this result. But it's a little bit nasty. Okay, so let's actually assume that we've got an interior maximum. So we write now we've got exactly the same situation as we had previously. We've got first derivatives, which is 0. We've got second derivatives, which are negative semi-definite. And the only thing is that because this function's a little bit more complicated than our previous one, we're going to get third derivatives. Things are perhaps not quite as simple. But let me tell you, so we've got dz is equal to 0, d2z is less than or equal to 0. And what we're going to do is, as before, z's defined on 2 copies of our domain. So the tangent space has tangent vectors that are sort of tangent vectors at x and tangent vectors that are tangent vectors of y. And we can use those. And we are going to, so here's, you know, x and here's y. So vectors here. So maybe if we have something like this, and we can either do these separately or we can do them together, just like we did in the previous one. So in what we find here, first thing I'm going to use coordinates where one of the coordinates, which we'll call En, is given by y naught minus x naught divided by y naught minus x naught. Okay, so, and this will be on both of these tangent spaces. So there'll be this so there'll be sort of this En there, and then there'll be all the ones that are orthogonal. And the reason why we do this is because this nicely breaks up the derivatives of this z, because we have these terms there. So our first derivatives of z So let's look at for I not equal to n, then in a direction that's purely at x, so I'm going to write dEI 0 of z. This is going to be, okay, so we don't get any derivative of these parts here, but we need to take derivatives of this and this and this. And so what we find here is that this is minus dEI den. So using these coordinates, we can see that this term here is actually like a derivative in the direction en. So it's w of x minus dEI w of y minus dEI w x divided by y minus x. And this is all at x naught, y naught. And for I equals to n, we have den naught of z. And this picks up a den w of x. And this picks up the derivative of the this sort of one-dimensional term at the end. So here we have phi prime. So the reason why we didn't get any phi prime in the first derivative here is because y minus x remains constant if we're sort of orthogonal to en, if we're taking derivatives that are orthogonal to en. And similarly, we can do the derivatives in with respect to the tangent space at y. So we get d0 EI of z. And this will be we get a change of sign, den w of y. Sorry, this is a plus. And finally, this one, whoops, this should be EI. Minus v prime. Okay, and now these derivatives are all 0. And we can also find second derivatives. And I'm not going to calculate them all, but let's call this selected second derivatives. And So we'll firstly find that d2z acting on EI, 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 EI. This is for I not equal to n. This is going to be something like this. So there's ice derivatives and there's the n derivative. And very similarly to what we did in the previous proof, we've got a en and a minus en here. And what's going on inside this second derivative is just as we did in the previous proof. This combination of tangent vectors deals with the cross terms in a very nice way. And for us, it turns out that this is dn, 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 so a third derivative in purely en directions. And then you notice that right at the end, this is just where we have the second derivative of our one-dimensional term. All this we take and we calculate a sort of a PDE for Z. So the details here are kind of not too bad, but long. So we find that dz, dt, and then we use the equation for w, and we take a derivative of that. So we find that, for example, ddt of say diw is equal to Laplacian of diw plus 2 dkw dk diw. And let me just let your imagination fill that in. But what comes out of this is this rather nice equation, and we can find that this is given by second derivatives in precisely these directions that we've chosen here. En minus en, en minus en, plus some second derivatives that are in these directions here, ei, 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 and this actually is occurring as a sum from 1 up to n minus 1. Okay, so those are the second derivatives, and there's some second derivative of phi here, and then there's a bunch of terms which are somehow like first derivatives. So now I'm getting a little bit sloppy, and I'm just going to write dz for any first derivative terms, because they're not going to matter because those first derivatives are 0. And we're going to get a slightly weird term here, which is fortunately strictly negative. Some other dz terms here, and then we get the derivative in time of our function phi. Okay, so once we have that, we can use our assumption that we're at a maximum to get inequalities. Okay, so this one, or these terms here, are all going to be less than 0. So they just drop out. We've still got this term here. We keep that in. This term is a first derivative, so it drops out. But we keep this derivative of phi, so we can write so that's that term there. And similarly, we've got a -2 phi prime here. This term here is less than or equal to 0. Dz terms drop out, and we still keep our time derivative of phi. And fortunately, this term here is like a 2z. Well, let's write that down. This is a 2z minus phi prime, minus phi term times phi prime. Oh, 2 phi. It's plus 2 phi. And we assume that we're at a maximum where z is actually equal to 0. So here we get this really nice one-dimensional heat type equation, which we can indeed solve. So what we find here is that our modulus of concavity, which is sigma of ST, is a viscosity subsolution of d sigma dt is equal to this. Okay, and this one we can actually solve, or we can actually find really good solutions for it that have, you know, the correct behavior at the initial time. And so so we could either do this directly, or we could just actually go through all these calculations we've done and say that, well, if we're actually working in the one-dimensional case, then we wouldn't have thrown anything away here. So the solution for this one-dimensional equation will be like the relevant quantity for the one-dimensional eigenfunction. So it sounded a bit vague, so let me just write this down. So let F be a solution to the classical heat equation. So here df dt is equal to F prime. Then let's say I'm going to extend my domain here. So before we were just looking at a domain where S ran from 0 to d on 2, but let's symmetrically extend it to minus d on 2. And what we actually find it then is if we set phi equal to f prime over f, so this is the derivative of log f, and it turns out that phi will then satisfy this equation star. Okay, and you know, you might be saying, okay, that's all very interesting, but the point about this is that we know kind of everything about this heat equation. In particular, we know that the long-term behavior of this. So no matter what the initial conditions are, well, boundary conditions. See boundary conditions here. F of plus or minus d on 2 is 0. So once we've got those boundary conditions, we know the long-term behavior of this guy, which is that F of ST, it's exactly given by these kind of scaled trigonometric terms. So, you know, F can initially have whatever initial values you want, but you know, the Fourier theory tells you that all the parts that correspond to the larger eigenvalues in the spectrum actually, you know, they become less dominant, and it's really just this part that's the dominant behavior for large times. And so this means that we can choose, or this gives us what phi looks like for large behaviors, large times. So phi looks like minus pi on D tan of pi S on D. And this is, for positive S, this is always less than or equal to 0. Okay, so this tells us that because we've used this maximum principle on Z, we can show that Z's less than or equal to 0 everywhere. And then then we know this long-term behavior, so that particularly for large values of t, we have so we have v of st is less than this. Okay, and so this tells us that W is concave. Now this kind of tells you something a little bit more. So as S goes to 0, this is giving us a pointwise concavity estimate, but it's kind of telling you also that you have some sort of better estimate when your points are widely separated. So for example, if we look at the 2 points on the domain where the diameter is attained, then this term here is going to minus infinity. Now we know that we're kind of expecting du sort of goes to minus infinity here anyway, so that's not news to us. But it's also telling us that for all pairs of points, you can make some kind of estimate of the concavity in this sort of quantitative way. So that's the modulus of concavity approach. And, you know, it's somehow there's a lot of tricky calculations there that it's hard to explain what's going on. But yeah, maybe I'll just leave it for, oh, okay, let's see what the time is. Okay, so what I wanted to do tomorrow is give a little look at what's going on in a geometric setting. So when we're looking at, say, a domain with boundaries on a Riemannian manifold, and you know, there's a lot of this stuff on Euclidean domains, but it feels like a very natural question for manifolds, and it hasn't been studied so much. And just to completely spoil the punchline here is that what we find in domains with positive curvature is we find these kind of properties. However, on domains with negative curvature, like domains in hyperbolic space, things can really go wrong here, and we don't find this at all. And so we've got a counter. We can construct a counterexample here that kind of shows how this all breaks down in negatively curved domains. So that's what we're going to do next. Yeah, is there any questions or, you know, maybe comments?